So today I'll be talking to you about enabling the AI revolution. And as you can imagine, there's humongous efforts inside AMD around the subject, in particular with regards to scaling our flagship GPUs and AMD's public energy efficiency goals. I think it was 30x by 2025, which we achieved, and there's been new ones published for 2030. But that's not what I'm going to talk about. Sorry, it's all awesome work, but what I'm going to talk about is I want to cover trends and the industry dynamics that are truly picking up right now, and that are foremost, I want to provide you with food for thought. So for the DAC community, what are potential areas of future focus? So in other words, more challenges and observations rather than solutions to be presented today. So I can't talk about AI without starting with a short disclaimer first. And that's because there are many viewpoints. And you might wonder, why are there viewpoints around AI? Well, I think it's twofold. Firstly, it's an empirical science, so it's not fundamentally understood. That means we run tons of experiments, we try to observe patterns, we try to derive scaling laws, but we don't fundamentally understand it. And secondly, AI research is generating an information bandwidth which is just truly beyond what individuals can observe. I don't know how you guys are coping, but I certainly am saturated by the end of the day. There's more AI research papers that I can ever digest in a day. So by the end of the day, I think what most of us do, we follow our favorite AI researchers whom we trust, and they all have different viewpoints, right? And that leads to different belief systems and bulls and bears. And that's particularly evident in this whole discussion around artificial general intelligence, or AGI for short. So you have the bulls, which I'm showing here in blue, right? The bulls say AGI is possible through scaling models. You make them bigger, you throw more compute and more data at that. And this is fueled by the imagination of millions, and it's fueled by the fear of being left behind in this whole race towards acquiring the superpower, right? Then the bears, on the other hand, they have a very different perspective, right? They're saying scaling AI through exponentially growing compute and data is not really making the model smarter. They just memorize more, right? They just memorize all the answers, but they don't really get the capability to generalize, to derive the concepts. Furthermore, LLMs, it's just next word prediction. All they do is they hallucinate the most likely word given the training distribution that they've seen, right? Now, reasoning models are a real step change. They're so much better, but they can still catastrophically fail on simpler tasks. I'll give you a couple of examples, right? There's the internet meme around how many R's are in the strawberry. I mean, you've all seen this, but I want to give you the example of chess, right? So the latest models still fail to win at chess, right? And okay, admittedly, chess is not a simple task. But if you think back, it was IBM's Deep Blue in 1997 which beat the human grandmaster at chess, right? That was 3 decades ago, right? And these latest models can't do it. Furthermore, latest models still fail to follow the rules at times, which is clearly showing that they lack the fundamental understanding. Now, I don't know where you are on the spectrum between bull and bear, and it actually doesn't really matter. I think this whole notion around AGI, that is a key component that fuels the investment that's going into the industry. Right? There's massive amounts of private investment, but also increasingly governments are investing, the whole sovereign AI efforts. Right? In the US, you have Stargate, of course. In Europe, we have the gigafactories. There's so much money put into this. And with all that money, it almost becomes like a self-fulfilling prophecy, right? Because that money will pay the smartest minds on planet Earth to work on these problems. And what that will do, it will accelerate everything. And that's what we observe, right? So when you look at the evolution of AI, the rate of innovation is accelerating. So it took 20 years to get from perceptrons and MNIST handwritten digit classification to deep neural networks and ImageNet. Then 5 to 6 years later, you already had the transformers. 4 years later, ChatGPT. And since then, it's been a roller coaster, right? You have mixture of experts, state space models, agentic AI, multimodal, reasoning, agentic, right? I'm afraid to blink at this stage. It's such a roller coaster. And what happens is then that those innovations lead to new inflection points whenever AI is outperforming human experts. So with every new benchmark we introduce, every new challenge that we spell out to AI, the community focuses all their efforts on beating the expert level performance, right? Whereby this is basically accuracy at any cost. We throw all the compute, all the data at it. It's along the bull thinking from slide 1. So here we're showing the progress on the MMLU benchmark, and we'll talk about MMLU in a little bit. X-axis shows you the years since the introduction of the benchmark, and the y-axis is the accuracy, so higher is better. And the blue line is human-level performance. Each dot is a published accuracy figure for one of the latest LLMs, and you can see AI is just getting better and better until it beats the human. And that's when we hit the inflection point, new scientific discoveries. And with that, we find new application domains for AI. And again, we observed this already. To give you just a few examples, right? In 2018, Waymo deployed ride-hail, if you recall. It's the first commercial autonomous vehicles. 2021, we saw AlphaFold solving the 50-year grand challenge in computational biology of predicting protein synthesis, enabling drug discovery on a completely new level. Also, Copilot emerged. 2023, GPT-4 passed the bar exam. And in 2024, AI discovered better materials and enabled ultra-fast charging batteries. And you might think, hey, that's a bit niche-y now, but it's actually super important for enabling humanoid robots. So it is actually a very important discovery. Also, 2024, DeepMind released GenCast for weather forecasting. Supposedly, it can do 10 to 12 days accurately. Now, I'm not so sure about this one. At least in Ireland, maybe they haven't deployed it, but they don't usually get even a day right. In any case, no doubt we haven't seen anything yet. Many new inflection points displacing the old. So I took also a moment to check what were the inflection points we have seen in EDA so far. You tell me what I'm forgetting, okay? So I believe the first time a paper using CNNs arrived at DAC in 2017. I couldn't find any earlier ones, but maybe I missed it. Then you had Synopsys DOS-AI emerge, shortly followed by Cadence's Cerebrus, leveraging some level of AI assist for chip design. 2021 was the year for Google's Alpha chip, which was a real breakthrough. Remember Jeff Dean's keynote at DAC that year? He was showing off benefits of AI in almost all aspects of chip design, right? From architecture exploration to RTL synthesis, verification, place and route. He covered the whole thing. And over the last couple of years, really cool work around circuit foundation models, which introduce a real paradigm shift from previous AI for EDA approaches. And who knows, after this year's DAC, what I have to add to the chart for the next presentation. So in any case, there are many more inflection points coming. In particular, I think there are big things happening in healthcare, life sciences, code productivity tooling, computer graphics, robotics. Robotics gonna be huge. I can't tell you. My goal for next year is teleoperating my humanoid robotic avatar giving my talks. And I can actually stay back home in my pajamas and doing the whole teleoperating. No transatlantic flights anymore. It's gonna be awesome. So we're in for a hell of a ride in the coming years. And despite all the hype we're reading everywhere, Eric Schmidt says the AI revolution is underhyped, which find it a little bit scary, but there we are. So I'm all buckled up for it. So we're not done, not for a long time, right? There's still many, many challenges ahead, despite everything we've just seen, before we get to the stage where we actually have pervasive AI. So first of all, there are still a lot of algorithmic challenges. Just to begin with, let me tell you about a couple. For example, coming back to the point from the very first slide about scaling intelligence with LLMs. Can they really scale like the bulls claim? And how far do we get with agentic post-training and test-time compute, really? So post-training and test-time compute are the latest scaling dimensions introduced by reasoning models. You probably heard of them. All you need to know for the rest of the talk is that test-time compute refers to running iteratively inference to get better answers. Now, in any case, we've all seen these type of charts before, right? The scaling laws, up and to the right. So you have intelligence, model performance on the y-axis, and years on the x-axis. And models are just getting better and better. But how long will it continue? And we all know this is not going to go forever, right? It's like Moore's law chart like 10 years ago, right? And there's already early research demonstrating exactly the limits, some of the limits already, right? For example, this is shown in the chart here on the right-hand side. It's called plan bench. Let me explain it a little bit better. So you have correctness on the y-axis. Higher is better. And x-axis is the number of required steps in the reasoning process. Think of it as number of chess moves, right? So you would take on average 40 moves until you win. Or maybe you are better than that. So the different colors reflect different models. So you have standard LLMs, which are gray and light blue. They hover just along the x-axis. They're doing really poor. Reasoning models, way better, in orange and red, right? Now, look what happens with the number of steps, right? The model performance almost linearly tanks, right? So reasoning models are great, and they're so much better than standard LLMs. They scale, but they're limited by the number of reasoning steps. So there's actually a beautiful study from Apple Research on all of this that I highly recommend for further reading. Then there's a big challenge with regards to fairness in algorithms. To make the point, let me give you an example. These are drawings generated, I just use Stable Diffusion. Pencil drawings for engineers at different stages in their career. From computer scientists, I had them all plotted, including member of technical staff, principal, blah, 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 till fellow, senior fellow, CTO. And you know what? There's not a female in any of them. Now, the point is, it's not necessarily about diversity here. It's about training fairness in the algorithms. If the AI doesn't have it, it means that it might only consider a limited amount of options and might make suboptimal decisions, right? Like, I don't want to see 50% women here, but there's actually, I think, 23% graduating in computer science in the US. It's not even 20% there, right? So the AI will make wrong decisions. But there's more than fairness, coming back to potentially catastrophic failures. If you lump all of these questions together, the challenge is, how do we enable safe, fair, and trustworthy AI? By the way, the generated image here is the one that I generated for senior fellow about 4 or 5 years ago. So at least I got 20 years younger, and I don't wear bifocals anymore. So I won't have time to go through all the algorithmic challenges, but beyond scalability is also the challenge with regards to data contamination and complexity in eval. So data contamination refers to the fact when the next generation large language model trains on previously published benchmarks as training data. So they basically just memorize the answers rather than understanding how to solve the problems, right? It's cheating. Furthermore, the more capable the models get, the harder it is to evaluate. And that's why you see more and more companies actually doing internal evaluations. So you actually use humans to interact with an LLM to get a sense for how smart they really are. It's called vibe checking. It's like a job interview. That's what we're doing nowadays. And finally, the last challenge is the data wall, because we basically run out of data on the internet. There's no more high-quality data, and model performance is limited by the amount and quality of your data set. So how can we scale beyond this? Two big approaches. One is multimodal, for example, using audio and video data for training of your models. Problem is not that dense in information, in particular TikTok videos, perhaps. But the other approach is synthetically generated data, which most are doing already. So using other LLMs to train new LLMs. But there's only a limited amount of synthetic data that LLMs can actually ingest. Both help an awful lot, but it's not solved yet. But beyond the algorithmic challenges, there are also economic challenges, which ultimately translate into technology challenges for us, and that's where it gets really interesting. So, well, we talked about this at the beginning, just on the first slide. Humongous amount of investment is going into AI, but the truth is that the revenue is still lagging behind. Why is that? One of the root causes is the high inference cost. So the LLMs are really expensive cloud service due to the enormous compute and memory requirements. Anthropic, for example, used, I think, in 2024, almost half the revenue for cloud services. And what makes this worse is there's this race to the bottom dynamic for inference pricing. LLMs are similar in their capability, and they're easy to switch. As soon as there is a cheaper one, the end user will swap it out. So they're underbidding each other, and the prices are racing to the bottom. Secondly, you have this challenge that there's a very short time window only to amortize the large R&D cost. To give you a feel for it, I think GPT-4 was estimated to have cost between 50 and 100 million to train. Now, you release it, right? And as soon as there's a better model, you're going to have trouble monetizing it again. And then you have the open source models like DeepSeek and Qwen, which are closing in fast. So AI is already jaw-droppingly amazing at a whole range of tasks. I believe the key to unleashing the wider rollout, or the AI revolution, if you will, is to lower the inference cost. And that's down to us. That's down to all of you. This is where we can collectively make a difference. And before you ask, training is important too, but inference more so. According to some cloud service providers, inference is already dominating. I'm not sure that's true for all of them. But with the advent of reasoning models, with test time compute, this is clearly going to shift more and more towards inference. So inference is expensive. Is there actually scope to get more efficient? So I just want to give you a couple of examples to show you that this is 100% the case. There's loads of redundancy in there. So let's first look at power consumption. So AI runs, nowadays, the racks will consume megawatts, right? And we're changing the power supplies, going from 48-volt DC to plus minus 400-volt DC to minimize the resistive loss. It's crazy, right? And you know data centers require nuclear power plants at this stage, dedicated nuclear power plants. Now you compare that with the human brain. The human brain operates on 20 watts. I actually get by most days on a cup of coffee. So imagine we even, imagine how much redundancy is there. And Sam Altman actually said that a nuclear fusion breakthrough is needed at this stage to meet the vast energy requirements of the future. Now I could make a really poor joke about fusion cuisine, but I'll skip it. So there's an estimated 5 orders of magnitude in improvements possible. Let me give you another example. Let's take a look at the reasoning models again. Here, the chart for an OpenAI is 01 on AMD benchmark, which is PhD level maths. And you can see again, hey, beautiful scaling behavior. It just gets better and better. Compute on the x-axis, model performance on the y-axis. But the x-axis is logarithmic. And you all know that means exponentially more compute for a linear step change in intelligence. And the bears would clearly interject here. I mean, is that really intelligent? I don't know. But I found this beautiful example on Reddit. You should go and check it out. So a user asked DeepSeek R1 to generate a random number. And it thought about this for 96 seconds. And then you can show the whole reasoning trace, and it's beautiful. It goes on over pages and pages. I just have a really small version of it here. It's super fun to read, though. So it starts off with looking at popular numbers. People like 42, but that might be too predictable. Then it figures it could use a mathematical formula, sums of combinations of specific numbers. Then it changes the approach. Wait, perhaps it's best not to pick a number too far in the extreme. It picks 47, but then changes its mind again because it's too cliche. Then picks 63, but that's divisible by 7 and 9. It thinks of using the number of letters in the prompt, but is that fair? Then it drifts on using time as a seed, then picking a number that's not prime, but then remembers blah, 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 blah. It just goes on. And in the end, it picks 73 after 96 seconds. Wonderful example of overthinking. So if you want the reference at the bottom of the page. And the same phenomenon is visualized in this chart. Now, more seriously. The chart shows model performance on y-axis again for ARC AGI 1 and 2, which is probably the best benchmarking attempt at AGI. X-axis is logarithmic compute cost. On the left side is 10 cents. On the right side is $10,000 for a single query, okay? So the left side shows you the types of questions being used in the benchmark, just to give you a bit of a feel for it. So you always have like the 4 squares. The top 2 give you an example of what the AI is supposed to do. And then the 2 below the left side is the problem statement. And the AI is supposed to fill out the one with the smiley in it, the bottom right one, right? So for the top one, ARC AGI, you probably figured it out already. You have to add a yellow square in the open corner, right? And for ARC AGI 2, same story. You have these blobs with number of holes in it. And depending on the number of holes, you color in the blob in a different color, right? It's all very, very standard. So going back to the chart, what do we see here? We see 3 models from OpenAI. We have O4 Mini, then O3, and O3 Preview, and please don't ask me about naming conventions at OpenAI. I'm sure there's reason behind it, but I don't get it. So when you look at this, the pink lines is ARC AGI 1 performance, and the yellow is ARC AGI 2. So just looking at the pink, you can see from model generation from one to the next, performance really goes up, gets much better, basically solves it, but pretty extreme compute cost for solving that little puzzle in the top left-hand corner. $10,000 for a query, right? Then you look at ARC AGI 2, and the model performance doesn't get beyond 20%, doesn't really scale. $10,000 per query, right? So in terms of coming back to the point, there's lots of scope for improving efficiency. And François Chollet himself, who is the author of this well-known benchmark, he said new algorithms are needed to bring AI efficiency in line with human performance. So again, much scope here. Final point on potential scope of efficiency improvements, just look at connectivity. Neural networks, predominantly dense compute, that's down to attention, computing correlation, which grows quadratic with the length in the input sequence. Human brain is extremely sparse, mine in particular when there's not enough coffee. At any given instant, only a small fraction, 1 to 2% of the neurons are active. So I hope overall you find this, you're sufficiently convinced now that there's huge amounts of efficiency gains yet to be had. So up until now, we talked about this need for inference efficiency and potential scope. Remember, 5 orders of magnitude. Let's switch gear now and look at what has been done. And the answer is, of course, there's lots been done. There's been a huge amount of effort in regards to efficiency optimizations. So let's go back to the benchmarks that we had at the very beginning. I hope you remember the chart. So tracking model performance. This is only ever the first phase, right, of when we get the models to sufficient level of accuracy. The truth is that after that phase, there is a transition to the efficiency of optimizations for all of these benchmarks, where we try to reach the required level of accuracy with minimum compute requirements. The chart has a form of efficiency metric on the y-axis here, which I'll explain in a minute, and the x-axis is in years since the beginning of the efficiency optimization phase. And the efficiency optimizations continue until we reach the point where it becomes economically viable to deploy the model, and then we can roll it out. So this is a super interesting observation. We've been tracking this across a number of benchmarks. It's basically a way of tracking the algorithmic innovations. And there have been many, many, many of those. You have mixture of experts, recurrent neural networks, new attention variants, KV cache optimizations, small language models, which are distilled from larger ones for specific tasks, and hybrid models, just to name a few. So let's talk about how we measure this efficiency. We put a bit of thought into how benchmark this, and by the end of the day, we went actually with something quite simplistic, namely accuracy over parameters. And you might think this is naive, but we actually put a bit of thought into this. So firstly, because with operations, you always have that dependency on the length of the input sequence, and it's way more complex because it gives you an additional dimension that you have to benchmark across. Also, we wanted to keep accuracy in there. If we leave it out, then it's just top performance, and we would be missing a lot of the efficiency improvement. We don't need cancer cure performance levels on all of the tasks. Secondly, we decided to use multiple benchmarks, as different models demonstrate strengths on different benchmarks. But to make it then comparable, we had to normalize across the accuracy range. And that all of that has big limitations. Some of them are listed on the slide. But we still think that this worked out really nicely as a proxy to track efficiency. Perhaps something you'd like to adopt. So let me show you. So this is the first one is ImageNet that you all know. We're just looking at the pre-transformer generation. You can clearly see this pickup in efficiency on the y-axis over years since started the optimization phase that we have on the x-axis. By the way, we visualize the trend with a linear regression, not gone on this, but it shows the upward trend. MMLU, if you remember it from earlier, actually stands for Massive Multitask Language Understanding. That corpus contains 16,000 questions covering 57 subjects from politics to engineering. I picked a simple example here from engineering, which I thought you might like. In an SR ledge built from NOR gates, which condition is not allowed, A, B, C, or D? I'm sure you all know the answer. Again, you see the continuous efficiency improvement over the years. I give you another example, ARC Challenge, which has 2,500 multiple choice questions, but they require advanced understanding. You can't just memorize this. For example, which property of a mineral can be determined just by looking at it? Luster, mass, weight, or hardness. Again, steep efficiency improvement can be tracked over the years, here foremost thanks to recurrent neural networks. And here I gathered them all together in one single chart, normalized to when they got started and normalized to the accuracy range, and all approximated with linear regression. So it actually shows nicely there's a similar behavior across all of these benchmarks. Now, we certainly cannot predict the level of innovation we're going to see in the future. And maybe there are none, and maybe they are real game changers. But here's what we observed over the last 5 to 7 years, right? It's a nice way to characterize this evolution. So you might say, hey, we have all these software improvements. What do we need to do on the hardware side anymore? We might as well not bother. It's not true. We are not going to get 5 orders of magnitude out of the software. We have to turn over every single stone. We cannot afford to leave any efficiency gains behind. So we have to do it on all levels. Quantization and sparsity is a massive lever, and I'm sure most of you use it. Runtime, schedulers, and mappers introduce inefficiency. DeepSeek even customized their distributed file system to get more efficiency out, right? We have to do all of this. And then there's the hardware level. And while we're squeezing Moore's law for the last bits of improvement inside AMD, the biggest advantages will come from architectural innovations. This is my one marketing slide that I have. I promised Alex I won't have more than one. I'm not sure where he is at, but just want to be clear and acknowledge there's a huge amount of effort across AMD as a whole. Don't want to come across as just talking about my own stuff. So, which is all focused on maximizing inference performance and efficiency across the devices, leveraging latest technology nodes, advanced packaging, optimized device architectures across the entire silicon portfolio from cloud to edge. And then we've just released our efficiency improvements, results 30x by 25, which we achieved, and there's new ones. But in the rest of the talk, I'm just going to focus on a small subset on how we're going to go customization of compute architectures in AMD research. So, most effective trick in the book is customization of hardware architecture. Many are doing this, right? You have the hyperscalers like Google doing TPU, AWS Inferentia, then you have the likes of Broadcom building ASICs for OpenAI and Apple. You have the innovative work from Cerebras and Samba Nova. You have startups with full transformer ASICs from Edge, and then you have the FPGA-based approaches with Elastics and Positron. And Jason Kong is also active in this space, and Deming Chen. And this is a trend that only gets emphasized with reasoning models as inference becomes more and more important. So in research, we're working on exploiting this too. This is our Fin effort. While we could go ASIC in principle, we're with FPGAs, and that's not just because of our Xilinx legacy, but that's because we get a lot of flexibility and agility out of the FPGA, and it's a fast-moving pace. So we build custom inference accelerators where the hardware architecture is tailored to the specifics of a neural network, of a specific use case. So the hardware mimics the topology. Every layer is present. We allocate appropriate amount of compute resources, and then we can just stream the inputs in, and execution is triggered basically on arrival of the data. And that makes it super efficient. It makes it lower latency, right, because it minimizes the activation buffering and the energy as we optimize for on-chip data movement. Furthermore, data flow can adapt and scale to meet diverse performance targets, so I can downscale and remove parallelism to basically create a hardware accelerator with minimized resource footprint, just enough to meet the required performance. So this is also really great for efficiency. Here I'm showing one for 1,000 lookup tables, and the same neural network scaled up to 100 million inference per second. So you can, with 1 million lookup tables, so you can really scale the architecture up and down to what you need. So let me show you the benefits of the example on an attention block. So this is our latest work. So first of all, see all the white lines here between the matmuls, the shuffles, and the adders? That's all on chip, right? All data moves on chip from one operator to the next and is stored in these gray little on-chip buffers. Secondly, the matrix multiplies and the buffers are perfectly sized to the specifics of the neural network. You're going to get close to 100% efficiency. And finally, you can have fused operators. So because the execution is triggered by arrival of the data, you basically can start running the shuffle as soon as the first row comes out of the matrix multiply, right? So that brings lower latency, less buffering, higher efficiency. So we have now, this work was done in close collaboration with Microsoft as an evolution of our Fin effort in AMD/Xilinx and Microsoft's Brainwave effort. We basically converging the two of them. And here you can see our first experimental results for bird-like transformers, so very small ones, as a first proof point. They are given as a ratio to an A100 operated in mix 7 mode. And you can see for these smaller models, there's a nice benefit with regards to inference per second, latency, and performance per watt. I'm not saying this is going to work for arbitrary workloads or for large models, but for smaller models, there seems to be a real advantage, right? When the GPU is basically going to end up being underutilized. So early work, much more to be done. We'll open source and release all of this jointly later this year, and it's going to be called Brainsmith, so watch out for it. Then, I mean, I don't have to talk much about quantization because you're probably all well familiar. It's the fewer bits I'm moving, the better. There's a whopping 30x between FP32 and FP4. We basically just adapt the algorithm to use lower precision math for significant improvements in energy efficiency while meeting the minimum accuracy target. But downscaling of MAC data types is reaching an inflection point. I would call it Amdahl's law for quantization is what we're reaching now. So sole focus on this will lead diminishing returns, and non-gem operators start dominating. You can see this in the top left-hand chart. For Llama 3, 8 billion model, FP16 is the left bar, the right bar is int 8. The non-gem is shown in gray, and you can see how it's starting to dominate the compute. Because of this, we found ourselves slightly switching the focus. So from the specifics of the data type to quantization technique. And that makes sense, right? If you think of it, your model accuracy depends on the data set, which is fixed. It depends on your data type, which is going to give you diminishing returns. And it depends on your quantization technique. And they have improved so much. The latest post-training quantization techniques are brilliant. Let me show you an example of how much we're going to get out of this. Still work in progress, but check this out. It's a Llama 3.21 billion, notoriously hard to quantize. You start baseline BF16 at 8.9% perplexity, so lower is better for perplexity. With round to nearest, so brute force, casting the data types, accuracy is going off the cliff. It's useless, basically. It's only after applying these 3 steps of post-training quantizations that we can recover the quantization error. So my message here is don't give up too easily, right? Keep trying combinations of these PDQ techniques. And you can even get something like Llama 3.2 to MX in 2-bit data representations. And finally, there's sparsity. And as discussed in the intro sections, neural networks are very sparse. But sparse doesn't map very well to matrix or vector-based compute units. You're going to be very efficient. But again, with data flow architectures, once you actually unroll your neural network, you can sparse and trim individual connections. So that makes it way more efficient. And the nice thing is, when your weights are hard baked, it happens automatically through the synthesis process. And then the final one is the Logic Nets project, where we take the whole thing to the extreme, where we say basically a lookup table in an FPGA is a neuron. We design a circuit, we represent the circuit as a neural network in the training framework, let it learn the task. And if we get sufficient accuracy, we have maximum performance by design. And it gives you another factor of already the data flow accelerators. So let me just show you some results to show you what we can actually achieve. This is my favorite. This is the coolest use case from the world's largest hadron collider in CERN, where they're looking for the elusive particle, for example, like the Higgs boson. It's basically a needle in a haystack search at extreme scale. And they're producing 2.8 billion collisions per second, which results in petabits per second of data, requiring real-time inference for filtering. They do this with 10,000 FPGAs buried underground, 100 meters underground. Each FPGA gets a terabit, no, I think several terabits per second of data. And they need to inference at nanosecond latency. And that's where we work with them together. So we've implemented that with customized data flow accelerators on FPGAs. Then for the fun of it, we said, how small can we make them, right, with logic nets? How small can you make a neural network? This jet substructure classification problem from CERN. So we optimized the Vasur out of it. The accuracy is not that great anymore, but still working classifier at 70%. We got it down to 30 lookup tables. That's like a 32-bit adder that small. And it's a full neural network, 3 nanosecond latency, 666 million inferences. And then I'm in this classifier. And I know you're going to say, this is a toy example, and it is. But it's so good for comparing, because you always have the results. So upper table are binarized neural networks, so heavily optimized neural networks, accelerators. And according to somebody else at Neurons, which we were absolutely delighted about, fastest MNIST classifier. And we said, oh, we got to try. Can we do even better with logic nets? And we can. so you're still going to get a dramatic performance, even from a binarized neural network to a fully sparse neural circuit, right? I mean, there's 1 to 2 orders of magnitude in throughput. And I'm putting this up there, of course, because I want to show off a little bit. But I think the bigger message here is really, don't stop optimizing, right? Even over a binarized neural network, you can still gain so much more efficiency. Lots of scope in there. Now, take a quick pause. Up until now, we talked about the importance of improving efficiency and how to lower it through extreme customization. But the problem is agility, right? We talked at the beginning how the pace of innovation is accelerating. So the time window that we have to customize the circuit is basically shrinking down to nothing, right? So the obvious thing to do is to build tool chains, which we've done. We've built end-to-end tool flows with our projects Fin and Brevitas. I'm going to keep this super brief because there's a more important point to be made. This is really automating quantization, sparsity, data flow generation, and the training tool is there to apply extreme quantization to it. And then what you get out of this is basically a netlist which you can run on an FPGA. So I'll skip through these because the time is ticking fast. So automated tool flow is all you need to take away with. And that's pretty effective for automating the customization process. But if there's a new model operator, a new attention block, someone has to manually sit down and write the kernel for it. It has to be added in the library for Fin and Brevitas, and that will become the bottleneck in the future. So we can certainly scale out with armies of engineers, but perhaps it's time where we really need to use AI more seriously in this whole optimization stuff. Perhaps AI can help unleash additional optimizations that we haven't foreseen to begin with. But I think foremost, it's needed as a productivity booster. Jeff Dean predicted this already in 2021. He said, being able to customize and optimize for specific workloads instead of building a more general purpose device can lead to significant improvements. And what I'm doing is I'm giving additional importance to this, an emphasis in the context of the industry today. So let me zoom out again. AI will roll out in big ways from cloud, where we have the large training workloads and the LLM inference. The next wave is already happening with enterprise and AI PCs for co-pilot, code productivity, and hyper-personalized entertainment. The biggest wave is yet to come. That's in the embedded space. And this is where and how AI is going to go truly pervasive. There's so many use cases that we can't even imagine yet, from automotive, sensor intelligence, robotics, to medical. They're from self-driving suitcases to self-driving strollers. Be amazed about all the stuff that is coming our way. In any case, you often see in the keynote slides the chart on the left-hand side, right? Back to model performance on the y-axis over x-axis on time. And I believe the left chart is what will drive scientific breakthroughs, space travel, fusion technology, cancer cures, you name it. But I firmly believe that center stage is going to be the inference optimizations. That will get us to revenue-generating AI deployment. That will be the factor which will enable the AI revolution. I think AI capabilities, I really want to stress this, are already amazing, superhuman on specific tasks, without getting to AGI. I don't think we need to worry or concern ourselves that. It's the efficiency optimizations which are really the key here. So in summary, AI is disrupting many industries today and many more to come. Watch out for my avatar next year. We talked at length how inference efficiency has plenty of scope to improve. Remember the power consumption and the cup of coffee. It must get addressed on all levels. There's a lot happening on the algorithm levels, like our recurrent neural networks and MOEs, but we can't afford not to do everything we can on the hardware side. We have to address it on all levels, and customization of accelerators is a humongous opportunity for all of that. We showed an end-to-end flow on how it can be done with Finn, Brevitas, and Brainsmith in the future. But there's a huge opportunity in exploitation of customization and the associated tooling. I would argue that design automation today is more important than it ever was. And I believe to keep up with the rate of innovation, to provide the necessary agility, leveraging AI becomes a necessity in the future. Now, that's it mostly from my side. I hope you found this helpful. My main aim here was to provide some food for thought about problems the community can focus on in the future. And with that, I'm happy to take any questions, perhaps in the break or something, because I know we're already coming to the end. So thank you so much for your attention.